In any refinery, chemical plant, or petrochemical complex, there's one process that's used time and time again to convert raw materials into usable products. This process is called distillation. Raw materials like crude oil, once considered a nuisance substance, can be separated into gasoline, lubricating oils, and feedstocks that eventually produce plastics and synthetic fibers. Seawater, the most abundant substance on Earth, can be distilled to remove magnesium and rare earth metals that are essential in the manufacturing of silicon for our computer chip industry. Distillation is used in literally hundreds of different ways to separate raw materials into products that can be sold or further processed. But how does distillation work? And how is the process controlled to create the desired end product? To answer these questions, we need to start by looking at the building blocks from which all substances are made. These are atoms, the smallest components which make up all things. Atoms have a natural affinity for one another, which causes them to join together and form what we call molecules. If you could look at crude petroleum, for example, with a strong enough microscope, you would see that its molecules are composed of hydrogen and carbon atoms that have bonded together in different shapes and sizes. This is why petroleum products are called hydrocarbons. This methane molecule is a small or light hydrocarbon. It contains 4 hydrogen atoms and 1 atom of carbon. Natural gas that is used for heating our homes is mostly methane. Butane, on the other hand, is a larger or heavier molecule than methane. Butane is made up of 10 hydrogen and 4 carbon atoms. In order to make useful products, raw materials like crude must be separated into fractions or cuts that contain similar types of molecules. One way to separate these molecules is by heating them. Let's look at a very simple example of how this works. Assume this vessel contains a liquid mixture of 50% pentane and 50% hexane. A pentane molecule is lighter than a molecule of hexane because it has fewer hydrogen and carbon atoms. When heat is applied to this mixture, the lighter component, pentane, starts to boil off before hexane because it takes less heat energy to move light molecules into a vaporized state. So the vapors that rise to the top of the vessel are rich in pentane. We can feed these vapors into a condenser, cool them, and form a new liquid. This liquid, like the vapor condensed to form it, contains mostly pentane. The liquid that remains in the vessel now contains a high percentage of the heavier component, hexane, because most of the pentane has been boiled off. This is essentially what happens inside a distillation column. When heat is applied to a liquid mixture of components, the lighter molecules vaporize and move to the top of the column because they boil at a lower temperature than the heavy molecules. The vapors are cooled and condensed back to liquid to form a product that contains mostly light components. The heavy components remain in a liquid state because they have a higher boiling point temperature. This liquid works its way to the bottom of the column where a heavier product is formed. Distillation uses heat to separate a mixture of components by their respective boiling points or boiling ranges. Although the products produced in the distillation process are seldom 100% pure, each fraction is made up of molecules with similar boiling points. The type of material present in the feed determines what kind of cuts or fractions are produced by a particular distillation column. Some columns, like this crude distillation unit, separate a feed into several different products. Other columns, like this depropanizer, separate a feed into just 2 products. Most of the products made in a refinery or a chemical plant pass through several distillation processes. Each distillation stage further refines and purifies the product. Some process streams are sent through additional reaction steps or processes. These processes actually change the structure of the molecules to produce a more useful product. An important thing to remember about distillation processes is that very few columns operate independently. Most columns depend on upstream distillation products for their feed, and the products they produce are frequently sent downstream for further processing. So poor quality in one product stream can cause major problems throughout the entire plant. It's time now for you to work through the exercises in section 1 of your workbook. You need to complete these exercises because they contain information not covered in the video that you'll need to know as we progress through the program. So go to your workbook now, and we'll return in a few minutes. A key variable in any distillation process is temperature. In order to increase or decrease the temperature of any substance, we must add or take away heat. Heat is thermal energy. If heat is added to water, this energy causes the water's molecules to move faster, and the temperature of the water rises. Heat that increases the temperature of a substance is called sensible heat because it is heat that can be felt or sensed. If we heat water in an open container to around 212 degrees Fahrenheit, it will start to boil. And if we continue adding heat to the boiling water, it will eventually boil away as steam. But the temperature of the water does not rise above 212 degrees Fahrenheit. Heat that is added to a liquid already at boiling temperature is called latent heat. Latent heat is energy which is used to vaporize a liquid that is already boiling. It's called latent heat because it does not affect the temperature of the liquid. Let's consider how pressure affects the boiling point of liquids. Pressure can be defined as force per unit area exerted by a substance. Our atmosphere exerts a pressure of 14.7 pounds per square inch at sea level. This pressure is caused by the weight and movement of air molecules in the atmosphere. Another kind of pressure is exerted by a liquid's molecules as they attempt to escape into a vapor state. The pressure is called vapor pressure. In order for water in this open container to boil, its vapor pressure must equal the atmospheric pressure around it. The water in this container will not boil until its vapor pressure reaches 14.7 pounds per square inch. The vapor pressure of a liquid can be increased by heating it. At sea level, water's vapor pressure reaches 14.7 when it is heated to 212 degrees. At this temperature, the bubbles of steam exert enough upward pressure to overcome the downward force of atmospheric pressure, and the water boils. If the pressure against the water is increased to 20 pounds per square inch, the water will no longer boil at 212 degrees. More heat will be required to raise the vapor pressure of the water to 20 pounds per square inch, at which time boiling will again occur. Suppose the pressure against the water is reduced to 10 pounds per square inch. Now the water will boil at a temperature below 212 degrees. At this reduced pressure, less heat is needed to move water molecules into the vapor state. The important thing to remember is that the boiling point of a liquid can be increased by increasing pressure, or it can be decreased by decreasing this pressure. In the distillation process, we are concerned with the boiling points of a mixture of components and not a relatively pure substance like water. And each component in the mixture exerts a different amount of vapor pressure inside a closed vessel. For example, at any given temperature, a light hydrocarbon like butane will have a higher vapor pressure than a heavier hydrocarbon like hexane. This is because less heat energy is required to move the light molecules into a vapor state. Since butane has a higher vapor pressure than hexane, the butane boils out at a lower temperature. This explains why we can separate butane from hexane by heating the mixture and then condensing the vapors. Let's take a look at how pressure can be manipulated to improve distillation efficiency. In the gas space inside this container, 10 pounds of pressure is being exerted by hexane molecules, and 5 pounds of pressure is exerted by heptane molecules. These separate pressures are called partial pressures. The total pressure inside a closed vessel is equal to the sum of the partial pressures. So, the total operating pressure inside this container is 15 psi. Now, if we add steam to the system and remove some of the hydrocarbon gas molecules, the total pressure inside the container remains at 15 psi. The steam contributes 9 pounds of pressure, hexane 4 pounds, and heptane 2 pounds of pressure. Adding steam to the system reduces the partial pressure that is exerted by the hydrocarbon gas molecules. So, when steam is added to the system, the hydrocarbons react as if they were under 6 pounds of pressure instead of 15. With less pressure acting against the liquid hydrocarbon mixture, hexane and heptane will distill at a lower temperature. This is known as the partial pressure effect, and it is used extensively in refining distillation processes to reduce the high costs of energy consumption. Let's review some of the basic heat and pressure principles now and take a closer look at how they affect the distillation process. Stop the tape and turn to Workbook Period 2. One way to visualize what happens inside a distillation column is to follow the separation of a liquid mixture through a series of stills. Suppose our mixture is composed of 50% butane and 50% pentane, and we want to obtain a pure butane product. Butane boils at a lower temperature than pentane, so if we heat the mixture to, say, 185 degrees Fahrenheit, more butane will be vaporized, and the condensed vapors will form a liquid that's enriched in the light component, butane. We can further purify this liquid by placing it in a second still and heating it at a slightly lower temperature. At 172 degrees Fahrenheit, for example, the condensed vapors form a liquid that contains 75% butane and only 25% pentane. This is because pentane has a higher boiling point temperature than butane, so less pentane vaporizes at lower temperatures. If we continue passing the liquid mixture through a series of stills that operate at lower and lower temperatures, we can eventually isolate a fraction that contains mostly butane. Because each still operates at a lower temperature, less pentane is vaporized as we move from one still to the next. Let's reverse the operation now and consider what happens to the liquid in the stills when we increase temperatures instead of decreasing them. At 185 degrees Fahrenheit, we said that more butane is vaporized than pentane. So the liquid that remains after the mixture is heated is enriched in the heavy component, pentane. If we place this mixture in a second still and heat it to, say, 196 degrees Fahrenheit, even more of the butane will boil off than did at 185. This changes the composition of the liquid to 75% pentane and only 25% butane. By passing this mixture through additional stills that operate at higher and higher temperatures, we can eventually form a pure pentane fraction. Because each still operates at a higher temperature, more of the light component, butane, is boiled off in each successive vessel. A distillation column operates on a similar principle as a series of stills, except that the entire process takes place in a single vessel. Inside a distillation column, there is a two-way flow of fluids. Hot vapors rising upward through the column contact a cooler liquid called reflux flowing downward. This footage shows what the inside of a distillation column actually looks like. The column is sectioned into a series of chambers that are separated by trays. Liquid reflux moving down the tower flows across these trays into downcomers, which lead to the next lowest tray. On each tray there are a number of openings, like these risers and bubble caps that provide a passageway for vapors to rise upward in the tower. The vapors bubble through the liquid on each tray as they pass through these openings. The trays in a distillation column function much like a series of stills. Vapors rising up the tower heat the liquid on each tray as they bubble through it. This heat is sufficient to vaporize some of the lighter boiling range fractions in the liquid, and they pass upward to the next tray as vapors. At the same time, some of the heavier boiling range fractions in the vapor condense and fall back to the next lower tray. The heavy components condense because the vapors are cooled or lose heat as they bubble through the tray's liquid. As this vaporization-condensation cycle repeats itself, a more uniform fraction is gradually isolated on each tray. The composition of the fraction is determined by the tray temperature. At 185 degrees Fahrenheit, a liquid composed of 50% butane and 50% pentane develops on this tray. As we move up the column, the tray temperature decreases, so a lighter fraction is formed on these trays. This is because more of the heavy component, pentane, is condensed out of the vapors at lower temperatures. As we move down the column, the tray temperature increases, so a heavier fraction is formed here. At high temperatures, more of the light component, butane, is boiled out of the liquid. If we add a sufficient number of trays to our distillation column and keep each tray operating at a slightly different temperature, we can isolate what is essentially pure butane at the top of the column and pure pentane at the tower bottom. We usually consider a distillation column as being divided into two main sections. The part of the column below the feed tray is called the stripping section. In the stripping section, light components not wanted in the bottom product are stripped or vaporized out of the liquid flowing down the column. The part of the tower above the feed tray is called the rectifying section. In the rectifying section, heavy materials not desired in the overhead product are condensed out of upward flowing vapors. Let's take a look at how the whole operation works. The feed to a distillation column is often preheated by a furnace or a heat exchanger. When the feed enters the column, some of the lighter components immediately vaporize and begin moving toward the top of the column. The majority of the heavy components do not vaporize and begin working their way down the tower as a liquid. At the bottom of the tower, most of the liquid is removed as bottom product. The rest is sent to a reboiler where it is heated, vaporized, and returned to the column. These hot vapors control the temperature at the bottom of the column. The vapors from the bottom of the column begin moving up through the trays and heat the liquid feed that is coming down the tower. This heat causes light components that are wanted in the overhead product to boil out of the liquid. Some fractions desired in the bottom product are also partially vaporized from the descending liquid. So some components that belong in the bottom product are carried above the stripping section with the vapors. The vapors from the stripping section mix with the partially vaporized feed and begin moving through the trays in the rectifying section of the tower. The lightest vapors do not condense in the column. They go overhead to a condenser where they are cooled to form a liquid. Some columns process materials that will totally condense from the vapor state. In other columns, there may be some very light fractions that do not condense at all. These non-condensables are a valuable energy source and can be sent to the plant fuel system. The liquid formed in the condenser is usually stored in a vessel called an accumulator. Most of this liquid is drawn off as overhead product. The remainder is returned to the tower as reflux to maintain a liquid level on the trays and to cool the hot rising vapors. The liquid reflux controls the temperature at the top of the column. As the reflux begins moving down the tower, it cools the rising vapors and condenses out any heavy materials that belong in the bottom product. Now that you've seen how a simple two-product distillation column works, Let's take a look at a more complicated unit that produces several different products. Stop the tape and turn to Workbook Period 3. In any refinery or chemical plant, you'll find that distillation columns are designed differently to produce different kinds of products. The column shown here separates two products that have a very small difference in their respective boiling points. This is a difficult separation that requires a large number of trays, so the tower is very tall. This column is much shorter because the products it separates have relatively large boiling point differences and fewer trays are needed to make this type of separation. Distillation columns are often classified according to the operating pressures they maintain. Crude units, like this one, are often called atmospheric towers because they operate at or slightly above atmospheric pressure. Other towers which process very light materials may operate under hundreds of pounds of pressure. The high pressures are needed to keep the products in a liquid state so they can be more easily stored and transported. Many pressure towers are designed with narrow tops because there is less vapor-liquid traffic in this portion of the column, and this design helps maintain the desired operating pressure. And finally, there are columns like this one that operate below atmospheric pressure in a partial vacuum. Towers that operate below atmospheric pressure are called vacuum columns. When we reduce the pressure on a liquid, it boils at a lower temperature. Vacuum columns reduce the amount of heat that is needed to vaporize hydrocarbons because they operate at very low pressures. Vacuum columns are generally used to distill very heavy compounds that have very high boiling point temperatures. If we distill these compounds at atmospheric pressure, we'd need to use an excessive amount of heat in order to vaporize the large molecules. These high temperatures, in turn, could change the structure of some of these molecules, thus changing their characteristics. We can obtain a better and a more economical separation if we moderately heat the liquid and then feed it into a column that is under a vacuum. The reduced pressure allows the lighter components to flash out or vaporize the moment the feed is introduced into the column. Vacuum towers must be able to handle high vapor loads, so they are usually designed wider than other types of towers, and their trays are spaced further apart. Different types of internal hardware are used to control the downward flow of liquid and upward flow of vapors inside distillation columns. The purpose of this hardware is to maximize the vapor-liquid contact which is necessary for good fractionation to occur. This bubble cap has teeth or slots that are set below the level of the liquid on the tray. Vapors rising through these slots are broken into small bubbles before they pass through the liquid. By forcing the vapors to form small bubbles, the surface area for vapor-liquid contact is increased. Other types of trays include the sieve deck, S-section, and valve tray. They use different types of hardware to force vapors to bubble through the liquid on each tray. On each tray, there is an inlet and an outlet weir. These weirs act like dams to distribute liquid across the tray and maintain the proper liquid level. Downcomers provide a passageway for liquid to flow down the tower. The downcomers can be designed to provide single or multiple flow patterns through the tower. Some distillation columns use layers of packing instead of trays to promote vapor-liquid contact. The packing material breaks up the liquid so there is a large surface area for contact with the rising vapors. The operation of a distillation column requires auxiliary equipment such as furnaces, reboilers, and condensers. This auxiliary equipment is needed to vaporize hydrocarbons and provide a cooled, liquid reflux. A furnace uses burners to heat the feed as it passes through a series of tubes. The tubes absorb heat in two different ways. First, the tubes at the bottom of the furnace receive direct rays of heat from the burners. Then the gases and vapors formed by burning fuel and air are channeled into the top section of the furnace to heat other tubes. Reboilers and condensers are both heat exchangers. A heat exchanger is a device in which the heat from one fluid flowing through a series of tubes is transferred to another fluid flowing across these tubes. In this reboiler, the fluid to be heated is bottom product and the heating medium is steam. The steam flows through tubes inside the exchanger. The bottom product flows across these tubes, absorbs heat, and is vaporized. The purpose of heat exchange in this condenser is to remove heat. The product being cooled is hot vapors, and the cooling medium is water. The cooling water flows through tubes inside the exchanger. Hot vapors flowing across these tubes are cooled and condensed to liquid. Let's take a closer look at how towers are designed as well as some of the equipment used in distillation columns. Stop the tape and turn to section 4 in your workbook. The properties of a distillation product are determined by the type of hydrocarbons that are present in it. To ensure that distillation products have the desired properties, certain standards or specifications are set to control their composition. The products are then periodically tested to make sure that they are meeting these specifications. These tests are sometimes run automatically by instrument analyzers. In other instances, an operator collects a sample and sends it to a laboratory for testing. If tests indicate a product is not meeting specifications, operating conditions inside the tower must be adjusted to change the composition of the product and bring it back on specification. One way to analyze the composition of a product is to perform a laboratory distillation test. This test is performed by heating a liquid sample and then collecting the condensed vapors. The temperature at which the first drop of condensate is collected is called the initial boiling point. The end boiling point, or end point, is the temperature recorded when the last drop of liquid in the container vaporizes. A range of temperatures between the initial boiling point and the end point determines the product's boiling range. This sample carries an initial boiling point specification of 150 degrees Fahrenheit. If the product contains the desired proportion of light hydrocarbons, the sample should begin boiling at this temperature. Lab tests show the sample actually begins boiling around 125 degrees Fahrenheit. Since light components boil at low temperatures, this test indicates the product contains too many light fractions. Here is a sample with an end point specification of 475 degrees Fahrenheit. If the sample boils away at this temperature, the product contains the right proportion of heavy components. The actual temperature, however, at which the last of the sample boils is 500 degrees Fahrenheit. Since heavy material boils at high temperatures, the product in this example contains too many heavy fractions. Some distillation products are given a boiling range test. A boiling range test identifies both light and heavy components over a product's entire boiling range. In other process streams, there may be very small temperature differences between the initial and end boiling points. These streams generally do not contain a wide range of different molecular components. So the best way to measure the product's purity or specification is to identify the actual light or heavy components in the product instead of measuring boiling points. For example, this column is separating propylene and ethylene, two hydrocarbons that boil at nearly the same temperature. The lighter component, ethylene, is going overhead. Specifications call for a maximum of 3% propylene in the overhead product, but lab tests indicate the top product contains 4% of this heavy key component. So the top product is off specification because it contains too much heavy material. Most petroleum-related products release flammable vapors. The lowest temperature at which these vapors ignite is known as the flash point of a product. Flash point is an important specification for some distillation products. Products that contain mostly light components release flammable vapors at a lower temperature than heavy hydrocarbon products. Therefore, a relatively light product like kerosene will have a lower flash point temperature than a heavy product like reduced crude. Specifications on this product call for a flash point between 145 and 150 degrees Fahrenheit. The actual flash point is 125 degrees. This product is off specification because it contains too much light material. Many products must meet certain weight specifications. The lightness or heaviness of petroleum products is usually measured by comparing their weight to the weight of an equal volume of water. Two different scales are used to do this. The API gravity scale uses a reference in which 10 degrees API gravity is the same weight as water. On this scale, the lighter the product, the higher its API gravity. So relatively light products like gasoline and naphtha have a higher API gravity reading than heavy products like lube oil and fuel oil. Another way to gauge the relative weight of a product is by specific gravity. On this scale, water is given a value of 1, and products lighter than water have a reading below 1. When measured on a specific gravity scale, you can see that the lightest products, gasoline and naphtha, have the lowest readings. The color of a product will often indicate whether that product contains the hydrocarbon molecules that specifications call for. Heavy hydrocarbons like lube oil are dark, while light hydrocarbons like methanol are very light in color. Color tests are generally used to check for contamination of light products by heavy hydrocarbon molecules. Setting specifications for products allows us to control the type or range of molecules that are included in any one product. This is important because the properties of a distillation product, such as its boiling range, purity, color, or flammability, are determined by the type of molecules that are present in it. When a product is off specification, a change in tower operations must be made to change the composition of the product and bring it back on spec. This is usually done by adjusting the heat balance inside a column. This column is producing propane as the overhead product and butane as the bottom product. Lab tests indicate there is too much butane going overhead with the top product. The top product is off specification. One way to reduce the amount of butane going overhead is to reduce the heat input to the tower. This can be accomplished by restricting the flow of steam to the reboiler. Because butane requires more heat to vaporize than propane, reducing the heat input to the tower decreases the amount of butane going overhead. Another way to remove butane from the top product is to increase the amount of heat removed from the tower. We can do this by increasing the reflux rate. The downward flow of reflux condenses the heavier components in the upward flowing vapors. In this column, butane is the heavy component, so increasing the reflux rate results in a top product containing less butane. This graphic summarizes what happens when the reboiler temperature is decreased or the reflux rate is increased. Either of these adjustments will reduce the temperature inside the column. When the temperature falls, less heavy material rises up the tower. As a result, there is a decrease in the amount of overhead products produced, as well as a decrease in the percentage of butane going overhead. We get just the opposite effect if we increase the reboiler temperature or decrease the reflux rate. Either of these adjustments will cause the temperature to rise. As the temperature rises, more heavy material is driven up the column. This increases the amount of overhead products produced and increases the percentage of butane going overhead. Adjusting the heat balance so that a column will make more or less of a particular product is called changing the cut point. Although cut point changes are frequently made by changing the column temperature profile, they can also be made by adjusting the column pressure. Recall how pressure affects the boiling point of a liquid. In a vacuum column, for example, the pressure is reduced so that more vaporization will occur at moderate temperatures. So reducing the pressure has the same effect as increasing temperature. Consider what happens in the tower that is separating butane and propane when the pressure is reduced. The lower pressure allows more vaporization to take place, which increases the amount of butane driven overhead. The overhead product gets heavier and more of it is produced. So when we reduce the operating pressure, we get the same effect as we did by reducing reflux or increasing reboiler temperature. Suppose we increase the system operating pressure without adjusting any other variables. The increased pressure causes less vaporization to occur, so less butane will enter the top product. The overhead product becomes lighter and less of it is produced. We get the same effect as we would by decreasing the column temperature. Normally, we try to maintain the column pressure as low as possible within the design limits because this reduces the amount of fuel needed to vaporize the feed components. Let's take a closer look at how a distillation unit is operated to make cut point changes. Stop the tape and turn to Workbook Period 5. In modern processing industries, instruments are used to automatically sense, measure, and control operating conditions or variables in distillation columns. The use of automatic instruments allows us to continuously produce products that are on specification and at the same time makes it easier to monitor and adjust the distillation operation. There are 4 major variables or process conditions that must be controlled in any distillation process. These variables are temperature, pressure, liquid level, and flow. Suppose we want to control the temperature at the top of this distillation column. The first thing we need is a measuring instrument that can sense the temperature at the top of the column. Next, there is a transmitter that interprets this measurement information and sends a signal to a controller. The controller is programmed to maintain tower top temperature at a desired value called set point. If the temperature has deviated from set point, the controller sends a signal to a valve, telling it either to open or close. This changes the reflux rate to the top of the tower and brings the temperature back to the desired value or set point. In any control situation for any type of process, 4 things are necessary. First, there is a process variable that needs measurement and control. For each process variable that must be controlled, there is a measuring means, 1 or more instruments that can measure the process variable. There must be some kind of control mechanism to receive the measurement information and determine how it compares with the desired value or set of values. The control mechanism must also tell the valve what action, if any, it should take. And there is a final control element, which is usually a valve. The final control element makes the actual process change that keeps the process variable at set point. So 4 things are necessary in any control situation. These 4 elements are called a control loop. Let's look at some actual instruments to review how the parts of the control loop work together. Assume that the variable we want to control is pressure inside this distillation column. A pressure tap connected to the overhead vapor line is used to gather measurement information. This information is then sent to a transmitter. The transmitter interprets the measurement information on tower pressure and signals a controller. A controller compares this measurement signal with a set point signal that represents the desired tower pressure. A valve like this one is the final control device in the loop. This valve regulates the flow of vent gas out of the accumulator. If pressure in the column rises above set point, the valve opens to decrease pressure in the column. If pressure in the column falls below set point, the valve closes and pressure in the tower will build up. Let's take a look at some other common control loops in distillation towers and see how they work together to control tower operating conditions. Stop the tape and turn to workbook period 6. In this program, you learned that many common raw materials are made up of a mixture of different molecules. In order to produce useful products, we must separate these various molecules into cuts or fractions that contain the same types of molecules. This is the function of the distillation process. We used a series of stills to demonstrate how a mixture can be separated by distillation. The top stills operate at progressively lower temperatures, so fewer heavy components are vaporized as we progress up from one still to the next. This eventually isolates a light fraction in the top still. The bottom stills operate at increasingly higher temperatures, so more light components are vaporized out of the liquid as it is piped down to each lower still. This forms a heavy fraction in the bottom vessel. In a distillation column, hot rising vapors contact a cooler descending liquid on a series of trays. As a result of this contact, light components in the liquid vaporize and heavy components in the vapor condense. This cycle gradually isolates a different fraction on each tray. The composition of each fraction is determined by the tray temperature and the column pressure. Since the lowest temperature occurs at the top of the column, a light fraction is formed here. A heavy fraction is isolated at the bottom of the tower where the temperature is highest. In any refinery or chemical plant, there are many different kinds of distillation columns that produce a variety of products. While these towers may be designed differently and may operate under different conditions, the purpose of each tower is the same: to produce quality products that meet specifications. You learned in the program that when products are off specification, an operating change must be made to bring the products back on spec. This is usually done by adjusting the heat balance inside the column. If we change the amount of heat that is put into or taken out of a distillation column, both product composition and quantity are affected. You also learned that most tower operations are controlled automatically by control loop instruments. Temperature, pressure, liquid level, and flow are the 4 primary variables that affect the heat balance inside a distillation column. Control loop instruments function to keep these variables at a desired value or set point. This concludes our program on distillation principles and practices. You should work through the review and self-test in the workbook now. This review will help you to remember the main points in the program. Thank you for watching.